Thank you, Peter. Hello, everybody. Last afternoon, the last day of the conference, I'm usually tired and stupid at that point. I'll try to cheer you up. Get some attention. I'm going to talk about about black hole transition in quantum gravity. But first, let me say something to Harold to start with. First of all, congratulations. For me, Harold has always been a source of inspiration, mostly because of his insistence of not being sort of pulled out by theory and its development, but going back to the key conceptual questions. An attitude which, in my opinion, has often put Harold outside the mainstream and going his own way. That is the source of his incredible productivity and, at the end of the day, enormously influence on the field. I enormously respect that. I've always tried to find inspiration from that. A small personal thing, I owe to Harold many other things, including the honor or the burden, I don't know which one, of being the editor of this journal, which he passed to me, and I have to deal with now. Where I hope, my hope about this journal is that it could become a forum, more and more, of exactly a way of doing physics, which is not just doing technical hard calculation and getting inspiration from that, but also getting inspiration from insights into the foundation. So the message here is if you have a good paper with a good conceptual contribution, please send it to us. We're very happy to give space to it. All right, so to business. It's a black hole. I'm going to talk about black holes. As Renate said this morning, there's a GR conference going around. The relativity world is bubbling with excitement, happiness, all sorts of things are happening in general relativity. The amount of new data which is coming in on the strong gravity regime is wonderful, and the level of the new possibility of what can be done even theoretically are opening up. Everything which is coming out is dramatically confirming GR. Right? So in a sense it's completely disappointing, in another sense it's super exciting. There's nothing in the data so far which talk directly to quantum gravity. That's very clear. Even if there are hopes, much more than what a few years ago was, that we might get something relevant for quantum gravity in the short term. As far as quantum gravity, I fully agree with what said just a moment ago, Andy. We don't have a quantum theory of gravity. There are attempts. We heard from Renata this morning. Andy was talking about some ideas. There's this fascination with the ADS, CFT sort of miracle happening, whether it's really telling us something quantum gravity. There are different communities, each of which have different assumptions and beliefs which becomes dogmas within the community, and it's very hard for this reason to listen to one another. But of course we should listen to one. The solution is not there yet, and nobody has the answer in these problems so far. Now, I'm going to talk a number of results which come from loop quantum gravity, which, and not only, also from just classical general relativity, which support a possible story about black holes, which is relevant for quantum gravity, is relevant for information paradox. I will say something about it later on. And I think it's a scenario which has not been sufficiently considered in the past because it seemed implausible, because there were reasons to believe it implausible, but it is not. and it might change the discussion of how we think about black holes. So what we know about black holes, incredibly they are for real. When I was hired in Marseille, my director said, there are no black holes. These are just regular things. It was 50 years ago. Nobody would say that today. They behave exactly as predicted by general relativity, as far as we can see. And there are two things about them which we clearly do not understand, which are, of course, what happened at the end of evaporation. We sort of are all convinced, even if there's no empirical evidence, that the total result of the radiation and its back reaction is very plausible, very credible. So we give it for granted, which I think is okay. The black hole becomes smaller, smaller, smaller. And then some of us think, oh well, it'll just disappear into nothing. This is just, wishful thinking. Why should it? There's no theory whatsoever that predicts that so far, clearly. We don't know what happens. And there's consensus that's where we need a quantum theory of gravity to tell us something. And then, of course, we don't know what happened R equals 0. We take a starship, I go into a black hole, and cross the horizon. General relativity gives a very good prediction what happens for a while, and go to R equals 0, and then we don't know. So this is the causal diagram, the cardinal diagram of a classical black hole, as described by general relativity. There is some collapsing matter, there's an horizon, sky minus and sky plus, and then there's a singularity here. And there is no strong evidence for thinking that general relativity is wrong up to a part where definitely general relativity is wrong, which is that region up there. Okay? Quantum theory in curved space-time might tell us that there are problems earlier than that. I'll come back to that in page hour with related arguments. But that's where definitely quantum gravity comes in, and I think that's where the key open problem physical in quantum gravity we have. So quantum gravity is a big theory to be constructed on paper, and then concretely either we tell us something about the Big Bang, or we tell us something about what happened there. So in the future, it is side of the particles. Now, it's good to split conceptually this problem in two, what I call the A region. I mean, suppose you're here in space-time, and you want to know what happened next. Okay, you go in that region, generally doesn't tell you. Or suppose you're here, this is the B region in space-time, so you're far away in the future. The black hole has shrunk maybe because of Hawking evaporation. At some point, something happened. And this B region involves the horizon, the A region doesn't. So this is the terminology I'm going to use. And now let me come to the main thing I want to tell you, which is the main message for which I'm going to argue and tell you what are the somehow new technical results that support this. This is a possible scenario for what might happen in those two regions, which is the following, that there is a space-time region, so to say, where quantum gravity is relevant, after which you go back to a classical space-time where instead, here this is a tropical region, you have an anti-tropical region, and therefore bounded by an anti-tropical horizon, you have a black hole. So this is a scenario, and what I'm going to tell you is a number of recent papers and technical results that support this scenario from a variety of point of view. I'm going to tell you what are the objections which are in the literature to this possibility, why this objection had answer, and also what are the possible consequences of that. And this will be the speculative part, because it depends on much else, even possibly observation. So just a few, this space-time is characterized by a certain number of parameters. The main ones are this one, the black hole lifetime, so it's the advanced time from say, the collapse to when something happens. The white hole lifetime, which don't need to be equal, because model was studied they're equal, but of course they don't need to be equal. The mass of the black hole, space-time, the mass m, And notice, let me take away these things which are confusing, noting that there is no event horizon. There is an horizon, so as long as you don't, you're an external observer, you don't go over here, what you see is exactly a black hole in the same way in which is described by general relativity, but there's no event horizon. There is a horizon, there's a trapping horizon. Okay? We somehow all got from school this idea that the only strange thing that happened at R equal to m is to be an event horizon. That's obviously nonsense. It's the boundary of the trapping region. There's a lot of specific physics that happen there. It's not local exactly, but it's quasi-local. Just go in a region of the order. As soon as the curvature is not negligible, you see there that a little light, a little ball of light flashes and both things contract, not just one. All right, but there's no event horizon. It doesn't go to infinity. So the past of psi plus is a full space-time, which means, by the way, that the naive version of the information paradox has an obvious solution. The naive version being, oh, things, information falls inside, it goes here, it dies. Where does it go? Well, it comes out. Process here comes out. This is a naive version because the information paradox can be formulated before any quantum gravity region, and I'm going to address that later on. So information that enters the black hole escapes the white hole. This is a scenario that is not new at all. It's been developed by all sorts of people in the past. I'm not going through the history of all that. It goes, there should be also the name of Herod here. Herod, I forgot you.
It's not third line.
Oh yeah, there is, sorry, I was looking at the wrong person. In a number of versions. So this is it. Now, what are the elements of evidence for that, and what we know and why we're taking it seriously? There are three things we should see for this to be reasonable. What happened in the A region, in which sense if I'm here, if I go to R equals 0, I go from an attractor region to an anti-attractor region. What happened in B, which is a much more complicated story because I have an horizon that becomes a black hole horizon, becomes a white hole horizon. But also, and perhaps is what made this picture implausible until a few years ago, the classical region, all the white part, which is not the tunneling part, which is not the quantum part here. If this is classical, it has to satisfy the Einstein equations. If it satisfies the Einstein equation, this is let's say it's very symmetric. This is Schwarzschild. So you should be an extension of Schwarzschild. But you know the maximum extension of Schwarzschild is Kruskal. And in Kruskal, a white hole is before a black hole, not the other way around. So this seems totally silly as a possibility. And let me tell you why it's not silly. So I'm going to give you now three recent results regarding first this one, and this one, which make this fairly close. So first one, main evidence one, regards the classical part. The point is, let me go back, that there is an exact classical solution, the extension of external Schwarzschild, which exactly cover this, and is a black hole and a white hole. And the reason you don't see it in Kruskal is because the fact that there is a boundary allows to cut and paste Kruskal and obtain this. In other words, if quantum gravity allows you to violate the Einstein equations in a small compact region, okay, compact surrounding the black hole for a short time, then you can cut and touch the Kruskal and get exactly the space-time here. And the way you can do is here, take Kruskal, take another Kruskal, cut this region and this region. This is, say, some incoming matter. Here is null and some outcoming matter. And notice that this is T equals 0 surface, T Schwarzschild equals 0 surface. It's another one. You can obviously glue this ones. That's the same metric, the same electricity curvature. If you glue it, you get a space-time where is the outside of a black hole with a black hole in the past and a white hole in the future, around a region where you are violating the Einstein equations. So you can have a black hole there okay, blue quantum stuff, and then a white hole. This is our classical generativity of changing. Now, in region, so how do we go in? Forget the horizon, just think you're inside. If you forget the horizon, the question is how you go from a crucial region 2 to a crucial region, what it is 4, going through here. Now, this has been studied using loop quantum gravity in the canonical form for a while. There's a sequence of papers, and I would say the outcome of all that is 18. So last year, PRL and PRD paper, that is 3% here, who have shown that if you take loop quantum gravity and you use the technology used in loop quantum cosmology, so you exploit the fact that there is a high symmetry here, the symmetry reduced the theory, you do a quantization of symmetry reduced one, and then you import from the full theory some aspect of the full theory that tells you what are the correction you take into account. Then this is a black hole internal, which I copied here. You work on the foliation, which is the one given by the Schwarzschild radius, right? Which is the symmetric foliation inside, and you evolve through. And you can see that you go through a quantum. So this is a quantum function. You go with Hamiltonian that evolves you through that. You pass through a region of high curvature. The curvature grows, gets to maximum when it's Planckian, and then it comes down. Okay? So this is a simple classical effective metric that interpolates that one. The geometry here, the geometry of the surface, as you probably know, the geometry of particle constant surface inside a black hole is a cube. Right? It's S2 plus R. As time goes up, so as you move up, the tube becomes longer and it shrinks. So what's going on is that the tube becomes longer and it shrinks. In the classical theory, it goes to a line, and then it's a singularity. Effective geometry in the quantum theory, it gets to the point where the curvature is Planckian, and then it comes back and you open. And you are sort of in a time reversal version of the same story, and you move up. Of course, what is relevant physics is not the full story when you have a matter inside and you're cutting by what happened in the main region here. So what is relevant is just that part here. So this calculation is an approximation which is good when you are there, which tells you that according to loop quantum gravity, you're going toward a singularity R equals 0, if you're not squashed by the time forces, of course. You go through this tunneling and you come up, you find yourself in an anti-traffic region. And finally, I'm not in any sense giving you the description of the full calculation, but you can use the covariant version of loop quantum gravity, the covariant version of loop quantum gravity, namely speed form technology, to compute the full transition across this region. What we're trying to do now is to lower the D region, but this hasn't been done yet. And the way it works, let me just say a few words on the way it works, because that's somehow for all of you who are not familiar with quantum gravity. In loop quantum gravity, you do quantum gravity not at infinity, not from infinity, but from, you do the quantum theory of a compact space-time region. So you have an initial state, a final state, and you do want the Hawking sum of geometries inside with given boundary conditions, or with a given boundary quantum state. So what you do here is that you know the metrical side explicitly, so you know intrinsic and extrinsic geometry of the boundary. So you have a quantum state. You can write a coherent quantum state of the boundary. You have explicit formulas for computing the amplitude. And this formula, of course, you have it in some truncation. You have order by order in some truncation. We use the lowest truncation. This is the spin network that you use. This is a spin phone that you use, for very few that know something about the technology. And you compute an amplitude, which depends on what? It depends on the metric outside, which, as I said, depends on certain parameters. So you get a probability amplitude as a function of these external parameters. And the key of the story is that, in fact, contrary to what we expected before, because we had an argument that the black hole could make this transition already when it's still macroscopic at the time and spare from the collapse, the calculation seems to say no, absolutely. What you get is that the probability amplitude is not suppressed when the black hole becomes Planckian, which you say, all right, that's what any reasonable person would have suggested to start with, and it did, but that's exactly what comes in, which means that this may happen. Okay? So the theory says strongly that this may happen. The black hole starts at mass m, its whole radiation becomes smaller, smaller, smaller. At some point, it becomes Planckian, microgram, remember? Black hole, mass is microgram. At this point, the probability for it to make a transition to white hole is non-negligible, becomes a 4 to 1, it happens from the other side. So these are the three elements of evidence. The classical GR is consistent with these people, with this picture. The A transition is consistent with this people, picture, and the B region as well. These three things. Now, just a few details more. From what I said, this, if you start with a black hole of mass m, this turned out to be a cube because it's a Hawking time right at the end, unless it's a very specific technical. As I will show later on, this needs to be proportional to n4, which comes from analyzing what happened boundary here, but I'll come back. The curvature goes to a maximum and it comes back, but the radius is, okay, let me give you the geometry. If you take a foliation like this one, here you are in the symptotic flat space-time, you can hear this in the throat of the black hole, which becomes smaller and smaller when you move up. Inside, you have this long cylinder, which, as the foliation moves up, becomes longer and longer and longer, gets to a point, and then it comes back. Okay? With the radius, it becomes smaller, 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 and then reopens across the transition. What's the minimal radius? The minimal radius is the curvature is Planckian, and curvature is m over r cubed. So the radius is the cubic root of the mass, the initial mass of the black hole here. Remember that an old black hole, which has shrunk, has an inside which remembers the mass of the original black hole. That's important for all the story. What are the alternatives to this story? This is an often discussed picture. I do not want to spend much time on that, but I think this picture is completely meaningless. There is no theory whatsoever that tells us that something is going to disappear that. If that was what happened physically, it would mean that quantum gravity breaks T reversal invariance dramatically when quantum mechanics and general relativity neither does so. It would mean somehow, think of it backward in time. You start from Minkowski, you throw in some little Hawking quanta, and poof, you create an interior. This is forbidden by the same reason for which, for so long, people didn't believe in white holes. Because white holes come from a past singularity. What is a past singularity? Well, white holes are possible, I mean, just go back, because the past singularity of the white hole is just the quantum region which is the future singularity of the black hole. But if there is nothing here, how can this start? I don't want to go into that. I don't think anybody can strongly defend this picture, if not as an assumption on which do quantum field theory, which is what Bob Walden will do, and they're right in what they do, but they are not possibly quantum gravity. The other possibility is that you go into a white hole which is in another universe. This is the version with matter. This is, if you have the second universe there, this has been studied. But this doesn't include the possibility of evaporation. It's killed as soon as you keep okay evaporation. And then, for very long, I and many other people before me studied the possibility that you just have a full quantum region after the trapping region without an anti-trapping region. And I worked on that, and I'm convinced, I'm totally convinced now that this is not, none of these people work, of these pictures work. And the main reason is that, you see, this is an anti-focusing surface, but inside, the inside boundary is a focusing one. So it's unstable. The open quanta that go there, or anything that go there, make the energy momentum tensor goes up and make the future different here. I don't see that any of this picture work in anything. Good. So, objections. There are objections in the literature that we go through then one by one, and then spend time on the last one, which is perhaps most interesting. First of all, white holes are unstable. That's true. Classical microscopic white holes are unstable. What does it mean? Well, just look what happened to a white hole. Little perturbation here, goes here, and the white hole, whoop, classically becomes black hole. That's possible, right? That's crucial. So a white hole can become a black hole by its stability, classically. Unless it is Planckian. Because once it goes down to a minimal size, it has no more energy to radiate away. And if you want, quantum mechanics stabilizes it. If you want to think quantum mechanically, you have a two-state system. There's a probability one going to the other, probability the second going to the first. So you sit down on the minimal energy of the two. So quantum mechanically, strictly speaking, this remnant here is a Planck size sort of linear superposition. Second, this picture here, so the remnant here has a Planckian throat, very small, but a huge interior, right? Because the interior is the same volume as what comes from here. Very, very long things. This is exactly the bag of gold that we heard this morning from one, and that Banks and Steve Giddens discussed in the 90s. One of the reasons the idea was abandoned is a so-called phase-space problem. If there are all these possible states for a small thing, you have this huge phase space for a small thing with small energy. Why are they not produced by shaking hands or at CERN? The argument being, whatever is the probability amplitude, you multiply by the phase space, which is infinite. This argument is wrong. Banks already observed that. And clearly we see here it does not apply. And here we know exactly what's going on, because at the time this bag of gold were just hypothetical things. These are exact solution of Einstein equation. We know exactly what is going on. We are outside the quantum region there, in classical terms. We know exactly what's going on. The probability of producing something is not the phase-space volume times the transition amplitude. It's an integral of phase-space volume of the transition amplitude, of course. You have an integral that converges on the infinite space. And clearly, the probability of producing something very long goes down. By what? By locality, because this is a very, very far away. This the only way of producing a white hole with a very, very long tail is to go through this process here. A black hole with a very, very long tail having this transition, quantum mechanically of this transition, not from that. Our first models always have the lifetimes of black hole and white hole equal as the first approximation of our calculations. And the problems there that is information. If you think that the information that falls inside has to come out, and if you think, I'll come back to that in a moment, that the information that falls inside is the one that purifies the open radiation, which goes here, then you have a lot of information inside and a small throat. And you need a long time for it to come out. In fact, the old calculation, you can see on this paper here, 93, that says that tau must be of the order of m to the fourth, so huge, for the information to come out. And in fact, if you do the matching here in the volume, you get exactly tau to the fourth. So there's all the time for the information to come out. So the naive information loss problem is solved. So the information comes in and goes out. But as I said, that's not. The relativists have a certain difficulty of digesting that. You all keep saying there's no problem with information. Oh, think. No problem with information loss. Just fall inside here. But field theorists consider information problem not this one, another problem, which is a page version of the problem. So let me go into that. What is a page version of the problem? It has nothing to do with the quantum gravity region. It's before the quantum gravity region. Is the idea that if the number of states inside a black hole, the maximum number of states, is given by the area, because the area is the entropy and the entropy is the number of states. Remember that this is, I assume that in the talk of one this morning. If you assume that, then you have a problem which has nothing to do with the fact that the information falls here. Why? Because to purify the Einstein, the Hawking radiation here, you need enough states there, and as soon as you go to page times, halfway, when the area is reduced to half, you don't have enough state there. So you have to assume that the early Hawking quanta are the ones that purify the late Hawking quanta, or vice versa. So the Hawking radiation is pure by itself, and there are this. And if you assume that, essentially you get to the firewall. Why? Because then you have a pure state here, which means that when you come back, you have to be not correlated with the inside. So of course, we had from Planck, this starting point, that the vacuum is full of correlation. If you want to cut this correlation, you have to go very far away from the vacuum, put a lot of energy there, and you have the firewall. That's the non-trivial version of the information problem. But all this depends on the assumption that the number of states is bounded by the area. And I think there is a conceptual confusion here between two kinds of entropies. Careful, this is not the distinction that one was talking this morning. But I think it's much more clear. It doesn't require any I assume that, I assume that. That's the standard physics. And separate the thermodynamical entropy from the entangled entropy. I'll come back to this here. Take a system, okay, which interacts with an observer exchanging heat and work. These interactions are determined by the number of states inside. But if inside the system you have a little piece here, which is completely energetically isolated from the rest, this does not contribute to the counting of states. Okay? That's standard physics. If in the past this was not isolated and was entangled with the observer, then you can have an entanglement entropy between the observer and that. And therefore, a phenomenon entropy here, which is much higher than the number of states of the outside region which determine the thermodynamic entropy. So the thermodynamic entropy is determined by the number of states I can interact with, which are relevant with my interaction. I can exchange energy with. Okay? If there's something inside I cannot exchange energy with, this don't count for the entropy, but they can have been in the past entanglement to me. Now, you don't believe that if you assume that if you take a version of holography as your dogma because you believe in ADS, CFT, and so on. But you're creating a problem for yourself. This problem is not coming from physics, from geometry, quantum mechanics. In fact, from general quantum mechanics is exactly the opposite. I've discussed this here. The number of states on the surface, if local quantum field theory is true, there's a simple argument, rigorous argument, is larger than the number of states here, even if the area of this is smaller than the area here. Okay? Because it's smaller than the area here, which is larger than the area here. I'm not going through the full argument. This is standard locality in quantum field theory. So if you want to force yourself to violate locality in quantum field theory on the basis of the dogma that you put yourself, that the number of states inside is bounded by the area, you create a problem for yourself. You have to go the page wave. You have to assume that the early and late Hawking quanta are correlated to one another. You forget the simple possibility that you are in this situation here. This is the internal black hole. You cannot interact with it anymore. It doesn't count for your thermodynamic entropy. Thermodynamic entropy is, it has to do with what happened on the surface of the black hole, not what happens. Okay? So the page version of the black hole information puzzle is not generated by the physics of quantum mechanics. It's not generated by the physics of general relativity. It's generated by an assumption. I call it arbitrary. I know that there are people sitting here that consider them, as God. Namely, that the full number of states inside a region is bounded by the area, which takes for taking very seriously a possible model of how to do that. So this is the picture. The Hawking quanta here are not correlated to one another. They are correlated to what is inside. So at this point, the subtle version of the information paradox is not there anymore. So it remains the naive version, which is what happened when the information goes to the singularity. Well, it just goes through and comes out from the black hole. I think, how much time do I have? I think I'll skip this one.
You've got another
15. So let me skip this one. This was about the quantum effect of the tunneling, because what happens during a tunneling, a quantum effect is subtle, but it definitely requires a longer discussion. I don't want to go into that unless somebody will raise that, because there might be some, well, not going to that. So a few developments. So this is space-time in considering. Some more recent development, there's a number of them. I just picked the ones seemed the most interesting to me. There is a metric of this entire space-time, so the classical metric outside plus the effective metric through the tunneling, which is not too easy but not too difficult to write. You just patch and glue pieces. But you can do much better because you have the Hawking radiation and you have the back reaction of the Hawking radiation. You want to know what is the back reaction of the Hawking radiation on this metric. And this is important for redoing better the quantum calculation of this area here. There's positive energy going this way, there's negative energy going this way, even if the quanta are outgoing, but the negative energy goes ingoing. This is not with a star, but with a null shell coming in because the calculations are easy to do. The null shell sort of goes through the center, continues, and exit here. And so we can write the metric of all that. We can model the geometry of all that, because nobody knows how to do the full calculation of the back reaction of the Hawking radiation on the Schwarzschild metric. But you can model it. Essentially, you model this with just the outgoing energy this way, and use a Meridian metric, so a sort of Schwarzschild metric with varying mass. And what you get is the color is the Meridian mass, how it varies. Here there is a Hawking radiation going out, here there is the negative, corresponding negative energy coming in. It crosses the outgoing shell and it bounces out. And we were very confused at the beginning because this is negative energy, and then we see negative energy coming out. And in fact, this was a long calculation, and the answer is not. This is the Bondi mass, the result of a long calculation. The Bondi mass is the initial mass of the black hole. It goes down because of the ordinary radiation. It's still radiating, but then it goes down. So what is going on? What is going on is that the negative energy here crosses the bouncing outgoing shell. So we have positive energy, negative energy. It eats up the energy of the shell. So the shell comes out with almost all this energy eaten up by the Hawking Panta. And what about the Hawking Panta that cross? They cannot die here by causality, they're continuing. And then we were confused for a while, and we did the full analysis of what happened there. And of course, we couldn't do it unless we understood what happened in detail when shell cross. And that's not easy to compute unless you're here at Delft and you produce this beautiful formula, which is exactly the formula that gives you. This is a nice paper back in the 80s with Cleve and Gray, which tells you exactly what happened when two shell cross. So we use that, we discretize that, we did step by step, we use that, and we got to compute this thing here. And what happened is very beautiful. It is in that formula. Ted didn't realize that at the time. If you have some negative energy coming here, and it crosses this positive energy thing, it goes the other side and it's positive energy. So this is positive energy. So the picture is quite consistent. There's work. All this is very symmetric. The rotating case will be totally different. So unless we get to the rotating case, the physical one, all this is pretty, we have a cow, let's assume the cow is very symmetric. Now, a few words about the phenomenology. There's a lot of literature on the phenomenology of this stuff here, which consider both what we previously thought was the most likely case, that could be a transition already to macroscopic black hole, and the case in which these remnants are pungent. I'm not going to that. I just wanted to mention that there was an hypothesis that the transition might be connected to the fast Fourier burst, and a study about the transition being connected to very energetic gamma rays. The reason this is interesting is because if you go into detail, you find out that if these events happen at a distance, they are redshifted differently than usual stuff. And the logic is the following. If you have primordial black holes produced later by collapse of things are too big to get the transition now. So to see something, you have to assume that there were primordial black holes. Primordial black holes are more and more likely and considered plausible by cosmology. So primordial black holes at some point they decay. The point is that the time they take, proportional in cube or m squared, it depends on the mass. So the more far away they decay, the smaller they are. And therefore you have an effect, a distance effect, which is not there in the usual astrophysical effect, which flattens the redshift. Instead of the standard redshift, you have a flattened band. And this might give a smoking. So, for instance, SKA telescope is looking at these things here. But that's what I find exciting, and it's completely speculative, but I like it a lot. So it's very recent, this idea. And so suppose these things exist. So early universe, you have a lot of fluctuation, you have a lot of black hole form. Okay? That's what cosmology more and more consider. Some of this, great, goes through the Hawking evaporation, become white holes, and then have an M4 lifetime. So they're there for very long. So if this is the case, the universe is full of things which are microgram. Dark mass is a microgram. which interact only gravitationally. They behave like a particle, mass 1 microgram, microgram is my hair, which only interact gravitationally. So if this was the case, the universe would be filled by some matter which is dark. Right? Now, could this be one of the components of dark matter? I think it's an hypothesis to be considered. Of course, we have 20 hypotheses for dark matter, so this is the 21st. But it's intriguing. So the only calculation supporting this so far is the following. Now we are at the Hubble time from the Big Bang. So if there is this matter around, it should be created by black holes that have a mass larger, smaller, such that the mass to the cube is smaller than now because they have already evaporated. But the mass to the fourth is larger than now because otherwise the black hole had time to, the white hole had time to just disappear. So it's white hole at time to disappear. So this gives a bound of the mass, an upper, lower bound of the mass. But according to black hole formation theory, primordial black hole formation theory, black hole formed when the horizon is of the order of magnitude of the Schwarzschild radius. So this tells you when these black holes could have been formed. And you go through the calculation and you come out that they formed just after inflation, which is exactly when you expect a large amount of black hole to form. So there is a certain possible consistency in this story. Cosmologists are looking into that. There are possible reasons for which not to work at all. I give you one, for instance, this black hole, when they evaporate, they produce Hawking radiation, so they heat up, and they have to be many. So is this consistent with the standard cosmological story? I don't know, I'm not capable of doing this calculation. People are doing this calculation. All right. So this is my summary, and then I have a little coda with one more consideration. So my summary is super simple. What happened R equals 0, space-time continues from the tropic region to the antitropic region. Gravity seems to do this very naturally. The idea, by the way, goes back to the 50s to Singer, first one to suggest that R equals 0. He noticed that just by a minimal correction of the Einstein equation, you can go from, well, you can continue crystal into another crystal. What happened at the end of the operation? Just quantum entanglement of a white hole. Quantum mechanics allows things to happen unless there is something strongly forbidding it. You don't see anything that should forbid that to happen when you have a Planck-sized one. Little coda, just to close, that's my last slide. One observation about the physics of this thing here, which I like particularly. So suppose this is the case, and take a black hole, some mass if you like. So if you're an observer outside, you're looking at this black hole here, okay? From the moment in which you see a collapse to the moment in which there's no black hole anymore, it's just matter, the time is time cubed plus time 4, so n cubed n 4, so it's very, very long if n is just anything with it. So this phenomenon do a huge amount of time. What you see from the outside, this is in the kind of coordinate that Hera would think about. So this is a Schwarzschild radius, and let's say that this here is a Schwarzschild time, which I glue with a Schwarzschild time on the other side. So I'll draw the equal time surfaces in a moment. Suppose I jump into the black hole with a clock and go through this this path in space-time. So suppose I'm strong enough to withstand the very small squeezing in which I go here and come back. What is the proper time along this line? Well, it's a simple calculation, because this is just the time to fall from black hole to singularity twice, essentially, okay, which is given by the mass. So this one is of order n. For the sun is what, millisecond? So from here which is an event in space, to here, there is 100 billion years outside and 2 milliseconds inside. I'll let you digest this. Okay? This is just general relativity with a little violation of Einstein equation allowed by a chemical effect in quantum mechanics. Okay? Most of this is just pure general relativity. General relativity takes the usual intuition of time and dramatically upsets it. Okay? What would I see from here? From here, I see the matter. I see what I see in Schwarzschild order. Nothing really goes in the black hole in Schwarzschild order, right? They just come closer and closer and closer and closer. So if I use a foliation, which is this foliation here, this is the foliation that doesn't go inside the black hole, kind of foliation that Hare likes to use. What I see is just a matter of they're going there, and then there's a little quantum stuff, and then it just comes out. Because this point here just jumps to this point here in this variation, right? So I used to think at the beginning that this picture is totally different than the picture on which Herod is working on. But in fact, I don't think it is. If you allow yourself to consider that the actual time in which you think, when you think, allow me, like a particle physicist, is dramatically distorted by GR. So what is from the perspective of particle physics, what is going on here? What is going on here is that there is an incoming something and then an outcoming something much, much, much later, from here to here. And a long, long time in which you just get closer, closer, closer to it, where the energy of these things, either here or here, is dramatically blue shifted or red shifted, which is only an effect of the funny Lorentz frame of this frame here being very, very different than the proper Lorentz frame or something going in. But this extreme energy is just a matter of the foliation that you have chosen, because here you're in a foliation, in a Lorentz frame. I mean, this object here has an immense energy with respect to a Lorentz frame that's moving very fast, of course. Here there's nothing, no big energy whatsoever, nor there's a big energy whatsoever. It is here. All right. So I think that, in fact, the picture which Herod is working could be made consistent with this, provided that Hare addressed what he had not addressed yet, which is what happened at the end of the life of black hole, which is a genuinely quantum mechanical phenomenon, instead of trying to recover unitarity without taking that. So the interesting story, I think, is there. And all this is the difficulty of intuition in time, so please allow me to take self-promotion by showing here my book, Theory of Time, and this I, as class did a few days ago, is my gift to Hare. So please consider that time is so dramatic in general. Thank you very much.
Thank you, Carlo. I think we'll have a lot of discussion, but some of it will be during the coffee break.
Thank you. Thanks. So it seems to me that, sorry, okay, again. You started your talk with saying how important it is to keep thinking for yourself and blah, 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 etc. And I totally agree. And so I'd like to do some out-of-the-box thinking as well. And if you allow me, I'll read aloud a Facebook post from a friend of mine about the visual image of the black hole, which is right now behind me. He says, no, these are not visual images of the black hole. First of all, EHT, the telescope used to make the picture, does not capture visual light. It is an array of radio telescopes collecting data at wavelengths many orders of magnitude above those of visual light. The colors you see in these images are artificial representations of the radiation actually measured. They correspond, etc. And he says at the end, more importantly, though, the source of these emissions is neither the black hole itself nor its event horizon. Instead, it is ordinary matter swirling around a black hole and heating up. Black holes do not exist.
Well, what your friend said is up to the last sentence.
Actually, what he actually says is we can't be sure that black holes exist.
Yeah. What your friend said up to the last sentence is perfectly correct. And whether we call this seeing or not seeing is just, I think.
Yeah, so, but then, okay, I agree with you, of course.
Wait, I should not say I'm enormously impressed by the fact we have seen a black hole. I should say I'm enormously impressed by the fact that the huge telescope has collected data such that...
Yes, and I think that's very important to me. Sorry.
Such that what we saw is exactly what we computed 6 months before using classical general relativity in a regime of very, very strong field. Now, of course, black hole could not exist. It's also possible that electrons don't exist because there is something else that behaves like an electron but is a very, very different structure.
Yeah.
It's also possible that quarks don't exist. In fact, there is how it's called technicolor. I think that there definitely is something in the sky that behaves in a way which so far agrees with what is wonderfully predicted by GR, and I don't know any equally good theories of ours. So the best theoretical description and understanding of what we see in gravitational waves detection with this waveform and all the detail and in this picture is GR.
Okay.
More than that, I'll let the philosophers answer.
Thank you.
Hi, Carlo. Back to the basics, I like that. So 3 basic questions. First, do you have the stress energy tensor inside the black hole? Because you're talking about matching the energies around R equals 0. But of course, one would have to match the full stress energy tensor. The second question is the Transplanckian problem. So you are going from a black hole to a white hole and you show that continuous line where you are blue shifting in one side and red shifting on the other. It takes a long time, but still, doesn't that create a problem? Because on the blue shifting part, you are pulling all these states out of vacuum and then red shifting them, so making them large scale and observable on the other side. And the third question is, you keep talking about Hawking radiation, but I don't know, why do you call it Hawking radiation? It's not. Now you have a different structure. You have a black hole and a white hole. And particles are global. We can't talk of Hawking radiation being produced on the side of the black hole and something else being produced on the other side. So I don't know. I mean, of course, you'll get some sort of radiation because you have a highly curved space-time there. So the gravitational field of that combined system will give some, will make the vacuum at future infinity different from the one at past infinity. So you will get some particles, but it won't be Hawking radiation. In fact, I don't even think it will be thermal. So using that back reaction of Hawking radiation inside the white hole and the black hole seems like an assumption. I mean, one would have to calculate what you get out of that whole system.
Yes, everything you said is correct. I think it's 2 things. It's a matter of naming things and a matter of what are the things we name. So, and I think the key of the story here is approximations. So, the question, I'm a physicist, not a mathematician. So, I think that idealizations are good when I use an approximation where which is irrelevant in some regime. And in fact, everything I've said is it's typical of me. I put something somewhere. Thank you very much. So let me start from the last one and then I move backward to your question. Let me use this one. This is the horizon. In fact, here I was a little bit more careful, and the horizon is the boundary of trapping horizon, which is time lag, is not light lag. So we're already outside the Hawking calculation, right? However, I do think that these, the space-time here, just, if I do quantum field theory on a space-time where, because there's a little bit of energy momentum around the bound of the trapping horizon is time-like, but the area it's large, the curvature is small there. I do think that Hawking radiation, Hawking calculation is still valid as the first approximation with corrections. I want to be wrong there, but I have to be shown that I'm wrong because that's how physicists do. You have a you idealize a situation. So I think that there is some energy momentum tensor that flows there as predicted by Hawking, that the radiation here is at least close to thermal, not exactly thermal for the reason that you said, but this is a good approximation. Okay? So as a good approximation, I can use the energy momentum tensor which has been computed and defined in the literature, defined in books now, of the Hawking radiation. And I know what is the energy momentum tensor here, what the energy momentum here. And then with another approximation, I say, can I just move a little bit my metric to make it more compatible with that? So yes, at each step, I'm throwing away some story, so nothing of the Dalai situation is correct, but I'm doing physics. This is what condensed matter will do at every step of his life. Each one of these steps might be wrong, but it seems to be the best we can do at present, and please note that this has nothing to do with a general scenario here. This is the heart of computing the metric inside. The general scenario remains the same whether or not this calculation is correct. The interest of this is that because, you see, here is a tube, it's a long tube, and I said that the radius of this tube is the square root of n, but it's not. The radius is square root of n, but it decreases and becomes very small here, it becomes nearly Planckian here. So the B region is a hard region. It's where I want to do the calculation better. The B region is entirely Planckian. It's not the end of a cubic root of n cube. It's the end of a Planckian tube, which is much easier to deal with in the quantum theory of gravity. We really like Planckian.
We have 4 interesting questions. We're having 11 minutes for coffee. Thanks again, Carlo.